everyone. In this video, we are going to be talking about how to find horizontal asymptotes. So before we get started with that, I just wanted to take a minute to remind ourselves what horizontal asymptotes are. So I have this little picture drawn here with a green function, and then I have this dotted red line. And the dotted red line is the horizontal asymptote. And what horizontal asymptotes are they're just horizontal lines that functions get really, really close to but never touch. So as you can see, this green function, as we move to the right, it's getting closer and closer and closer to that dotted red line, but it'll never actually touch it. So it's pretty analogous to a vertical asymptote. The only difference is that horizontal asymptotes lay flat. They are horizontal from left to right, and then the vertical asymptotes stick straight up and down. So horizontal asymptotes, again, the function just gets really, really close to it, but never touches. And the equation of any horizontal line, any horizontal asymptote is y equals some number a. So for example, y equals 6 or y equals -2. The equation of a horizontal line will always start with y equals something. So that's a quick just refresh on what horizontal asymptotes are. And so now the question becomes, okay, how do we actually go about finding these? How do we find the equation, the y equals equation for a horizontal asymptote? And so there are a couple different ways we can do it. One way we can do it is just by looking at the picture we're given. So I have a picture right here of some function, this green function, and I have this dotted red line at a y value of 1/2. And the question is, what is the horizontal asymptote? And so now this might seem kind of obvious because you can just look at that and go, well, it looks like the green function is getting really, really close to that dotted red line. We know that that dotted red line is at y equals 1/2. So it looks like the horizontal asymptote for this should be y equals 1/2. So if you have the picture, then sometimes you can just look at it and you know. But then the question becomes, well, what if you don't have a nice picture? Or what if you're taking a test and you don't have access to a graphing calculator? Is there a way from the equation of a function we can figure out the horizontal asymptotes? And you'll find out there is. But so let's just say this equation, this green function right here, let's just say it has an equation that looks something like this. I just made that up. That might not match that green graph exactly, but just pretend that this is the equation of that green function. Okay, and then we want to figure out using the equation what the horizontal asymptote is. So there is something in this equation, there is some information that allows us to figure out what the horizontal asymptote is. So pause the video and see if you can figure out what it is about this equation that is going to tell us where the horizontal asymptote is. So to kind of see this, let's just take a look at this green function. So I want you to notice that when we are about right there in that purple area, the green function is kind of far away from the horizontal asymptote, right? There's this whole distance between them. That's kind of a big distance. But if we move a little bit to the right, say right here, the distance between the green function and the red line is a little bit smaller, right? The green function and the red line are a little bit closer together. And if we keep moving to the right, the green line and the red line are even closer. And if we keep moving to the right all the way over here, then they're even closer. So it seems like when x is around, like say 0, it looks like the green function and the red line are kind of far apart. The green function isn't really close to the vertical or the horizontal asymptote. But as x gets bigger, as we move to the right and x gets bigger, the green function is getting closer to the red line. It's getting closer to the horizontal asymptote. So from that, it kind of seems like this function gets close to the asymptote for really big x values, right? As x gets bigger and bigger, the green function and the red line become closer and closer. So that's an important piece of information. For big x values, that's when this function gets close to the horizontal asymptote. So now using that thing we've just noticed, let's now look at this equation. And let's start with the top right here, 4x squared plus 6x. When x is really, really, really big, say x is 100, 100,000, a million, which one of these terms on the top do you think is going to be bigger? Do you think 4x squared is going to be bigger? Or do you think 6x is going to be bigger? Well, let's say that x is a million. 6 times x, 6 times a million, that's 6 million. But 4 times a million squared, that's way bigger, right? I mean, that's like about like 6 more zeros. So it seems like this term, when x is big, this term is a lot bigger than the 6x. And then let's do the same thing with the bottom. When x is really, really big, let's say x is a million, which do you think is bigger? Do you think the 8x squared is bigger, or do you think the 5 is bigger? And maybe that one's kind of obvious. 5 is always just 5, but 8 times a million squared, that's again going to be some massive number. So it seems like when x gets really, really, really big, the 8x squared is kind of dominating on the bottom. And when x gets really, really big, the 4x squared is kind of dominating on the top. And so what I mean by dominating is that the 4x squared and the 8x squared become so much bigger than these two terms that the 6x and the 5 basically become irrelevant when x is really, really big. The 5 and the 6x are so much smaller compared to the other two terms that they basically become irrelevant when x is really big. So why is this important? Why do we care? Well, we noticed that the horizontal asymptote gets really close to the function when x is really, really big. So if we want to figure out where the horizontal asymptote is, it would make sense when we're looking at the equation to only look at the terms that kind of dominate, the terms that are more important for really, really large x values. We don't care about the 6x and the 5 when we're looking for horizontal asymptotes because those terms are really small. They're so small that they're almost irrelevant. So that means we only care about the 4x squared and the 8x squared when we're looking for horizontal asymptotes. So I'm just going to pick those two values out of the equation. I'm going to kind of isolate those. So I dropped off the 6x and I dropped off the 5. We just picked the dominating term on top and the dominating term on bottom. Okay, so I have y equals 4x squared over 8x squared. Can I simplify that expression at all? Well, x squared divided by x squared is just 1, right? So these terms cancel. So we're left with 4 over 8. And 4 over 8 is the same thing as 1/2. And 1/2 was exactly where our horizontal asymptote was. So what we just did is we just found where the horizontal asymptote of this function is using the equation. And what we did with the equation is we picked out the leading terms in the numerator and the denominator, because those were the terms that dominated when x got really, really big. So the reason that we're going through all of that is kind of the rationale behind our method for finding horizontal asymptotes. To find horizontal asymptotes of rational functions, we isolate the leading terms in the numerator and denominator and simplify. Again, because horizontal asymptotes, the function approaches them when x is really, really big. And when x is really, really big, we only care about the leading terms because they're so much bigger and more important, influential than the other terms. So this in purple right here is your process. This is what you are going to use every time you want to find a horizontal asymptote. So let's do a few examples here. We have 2 examples here. The first one is y equals 3x squared plus 6 over 2x squared plus 5. So we're going to use our method that we just discovered. We're going to isolate the leading terms in the numerator and denominator. So if I look at my numerator, the leading term is 3x squared. How do I know that's the leading term? Because it has the biggest exponent. Okay, the exponent on the x is 2. And now we also want to isolate the leading term in the denominator. In the denominator, my leading term is 2x squared. So I'm going to isolate both of those. So we have y equals 3x squared over 2x squared. And then next we just simplify. Well, x squared divided by x squared is just 1. So those cancel. And we're left with 3/2. So y equals 3/2 is the equation of our horizontal asymptote for this function. Let's do another example. So in this one, we have 2x cubed plus 5x squared plus 6 over 6x cubed plus 2x plus 9. Same process. We're going to isolate the leading terms in the numerator and denominator. So the leading term in the numerator is 2x cubed. How do I know that? Because the 2x cubed has the biggest exponent. The exponent is 3. whereas this term only has an exponent of 2. So it's not the leading term. The leading term is the term with the largest exponent. Okay, same thing in the bottom. 6x cubed is going to be my leading term because it has the biggest exponent. So I'm going to isolate those, 2x cubed over 6x cubed, and simplify. X cubed divided by x cubed is just 1, so those cancel. So I have 2/6, which is the same thing as 1/3. So y equals 1/3 is the equation for the horizontal asymptote of this function. Okay, we're going to do a few more examples because there's some other situations that are important that are a little bit different. So here's another equation. We want to find the horizontal asymptote, same process, isolate the leading terms in the top and bottom. So in the numerator, the leading term is 7x squared. In the denominator, the leading term is 4x cubed. So I'm going to isolate those, 7x squared over 4x cubed. Okay, and now we're going to simplify. So I have x squared divided by x cubed. So I can simplify that to be 7 over 4x, right? Because that's one of our exponent rules. If we have two things being divided that have the same base, we can subtract their exponents. So 2 minus 3 is x to the negative 1, which is the same thing as 1 over x. That's just a quick refresher on the exponent rule. Okay, so we simplify and we get this, 7 over 4x. Okay, what do we do next? In the other examples, the x is always canceled out, right? And then we were just left with a regular number like 6 or 5. But this time, we still have an x in here. But let's remember why we're using this process in the first place. So we figured out that when we're looking for horizontal asymptotes, we're looking for when x gets really, really big because the function approaches the asymptote, it gets close to the asymptote when x gets really, really big. So look at this expression right here and think about what happens to this expression when x gets really, really big. So say when x is 10,000, 100,000, a million, 2 trillion. When x gets really, really big, what is going to happen to this expression? Well, let's say x is a million. X is a million. We're going to have 7 over 4 million. Okay. And then if you put that into your calculator, you're going to get some really, really tiny number, right? It's going to be like 0.00 dot, 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 and eventually some other numbers. But it's going to be really, really tiny, right? What about when x is 5 million or x is 100 million? That number is going to get even smaller, right? It's going to be like 0.0000, a bunch of zeros. It's going to be some tiny number. And as x gets bigger, that number is only going to get smaller. So what happens in this situation is that actually the horizontal asymptote of this function is y equals 0. Why is it 0? Well, because as x gets bigger, this number gets so small that it's basically 0. Or to use the language of limits, it approaches 0. So as x approaches infinity, this expression approaches 0 because the number gets super small. So because it's approaching 0, that means our horizontal asymptote is at 0, y equals 0. Okay, now we're going to do one last example. And so we're going to try and find the horizontal asymptote. Similar process, isolate the leading terms in the top and the bottom. The leading term in the top is 3x squared. Leading term in the bottom is 2x. Okay, so I'm going to isolate those. Y equals 3x squared over 2x. And now we're going to simplify. X squared divided by x is just x. So we get 3x over 2. Okay. Again, the expression we get after simplifying still has an x in it. So what do we do with that? Well, this time the x is in the numerator. Right? It's in the top, not the bottom. But again, let's think about what is happening with a horizontal asymptote. Okay, horizontal asymptotes, we're looking for the places where x gets really, really big. X becomes some really big number. So look at this expression and think about what happens to this expression as x gets really, really big? Or what happens to this expression as x approaches infinity? Well, if x is 1,000,000, this expression is going to be 3,000,000 over 2, so 1.5 million. And then as x gets to, say, 100,000,000, then this is going to be 300,000,000 over 2. And then it's going to just keep getting bigger and bigger and bigger. Those are pretty big numbers, right? We had 1.5 million and then 150 million, right? This expression is just going to get really, really, really big. So it's kind of like the opposite of the last problem. The last problem, the expression was getting super, super small. But this time, it's getting really, really big. So what does that mean for the horizontal asymptote? Well, as x gets bigger, this expression is just going to keep growing. It's never going to stop. It's going to just keep becoming a bigger and bigger and bigger number. So what we would say is that the horizontal asymptote does not exist for this function. This function has no horizontal asymptote. Because remember, a horizontal asymptote bounds the function, right? The function never gets smaller or bigger than that horizontal asymptote. But this function, it just keeps climbing up. The y values just keep getting bigger and bigger and bigger. So that means there's no bound to it. It keeps growing. There's no horizontal asymptote that it kind of caps out at. It just keeps getting bigger. So the horizontal asymptote here does not exist. Okay, so I know that I just threw a lot of information at you, but I wrote out this table to kind of summarize everything that we've talked about. So hopefully this can kind of help you when you're doing these problems. So in AP Calc, there's really 3 situations that you need to know about when you're finding horizontal asymptotes. So the first situation is that the leading term on the top and bottom have the same exponent. If that's the case, then your horizontal asymptote is just going to be the quotient of the coefficients. So here's an example of what I mean. In this example, we have 6x squared over 3x squared. The exponent on the top is 2. The exponent on the bottom is 2. So that means the x squareds just cancel. And the horizontal asymptote is just 6 divided by 3, which is 2. So that's one situation. If the exponents on the top and bottom are the same, then that means the x's cancel and you're just left with the coefficients. Second situation is that the leading term on the top has a bigger exponent. Okay, so here we have 8x cubed over 2x. The x on the top has an exponent of 3, and then the x on the bottom only has an exponent of 1. So the term on the top has a bigger exponent. If that happens, that means there is no horizontal asymptote. It does not exist. I wrote infinity here because some people will say that the horizontal asymptote is infinity. I think it's more proper language to say that the horizontal asymptote does not exist, but either way, there is no horizontal asymptote. There is no cap. This function just keeps growing. And then the third situation is that the leading term on the bottom has the bigger exponent. So here we have 6x to the 4th. The x has a 4 on the bottom, and then in the top, the exponent is a 2. So here, the leading term on the bottom, x to the 4th, that's the bigger exponent. If that happens, that means that your horizontal asymptote is just going to be at y equals 0, because this expression is getting super, super, super small. So those are really the 3 situations that you're going to run into. If you just do a bunch of practice, memorize this table if you think it's going to help you, it really won't get much more complicated than this in AP Calc. So try to get a handle on these 3 situations. You can make up your own rational functions and try to find the horizontal asymptotes of those and then graph it on Desmos if you want to check yourself. But it won't get too much more complicated than this. So I really encourage you to get comfortable with this table, these 3 situations that we talked about, and then you should be good for finding horizontal asymptotes. So I hope that video was helpful. If you have any questions, as always, please leave them in the comments and don't forget to like and subscribe. Thanks.